Okay, so it's a wealth of resources, not just in CFD, but in structures, in electromagnetics, anything you're interested in. All of these Ansys-based simulation tools. There's a bunch of materials, a bunch of tutorials, and you can really go into the industry with a kind of commercial level understanding of these products if you go through all of this material. So it's really valuable. It's free for anyone, whether you're part of a uni or not. So yeah, jump on here. The tutorials for what we're covering yesterday and today are on here. And you can, when you get the slides, they'll show you which exact tutorials to go through, but it'll be in here, fluids. There'll be some in the turbulence. I'd say fluent meshing and space claim you'll want to go through. But yeah, that'll come with the material that we send through. Okay, so let's get started then on today. I'm going to carry on from where Hashan left off yesterday. And what we're going to do, we're going to kind of similar to Hashan, we're going to do a lot of it based on in the Fluent window. So we're going to set up a model, and we are going to get it running, and we'll talk you through that as we do so. And then we'll go through some slides and take you through things like turbulence. We're going to look at things like heat transfer. We're going to look at some solver settings. All of the different ways you can find errors in a CFD simulation, because there's a lot. And then we're going to go through some post-processing, some simulation review. And if we get a chance, I'll take you through some more advanced models that we've built here based in adjoint solver and based in things like overset meshing. Okay. So like I said, the first thing we're going to do today is we're going to set up a CFD run of a FSAE vehicle, or the front end of an FSAE vehicle. So I take it this is the one that Hashan went through and meshed yesterday. So we're looking at basically just the front wing and the wheel. So we might run one of these half car, quarter car models if we're really just trying to do a deep dive of what happens after the airflow hits the front wing and what it does with the wheel, whether we can direct flow around it, etc., things like that. We might do something like this because we're limited on computational resource, right? So to do a full car model, there's a lot of elements involved, and if we don't have the computing power, we won't be able to run a full car simulation. So we might do a deep dive of a front wing wheel interaction scenario just like this to get a better understanding with limited computational resources. And that's just using engineering judgment. Okay, so we've got our quarter car model, front wing, should have a symmetry plane in the middle. So let's look at the size of the domain, see if the size of the domain is good enough. So it's quite a small domain. If we were doing a full car model, we might want one a bit bigger, but because our region of interest is mostly in here, I'd say this is probably a decent sized domain for us to get started with this one. And then, so once we've got that, we're going to look at our mesh. We're going to perform a mesh check, make sure that we've got a relevant mesh, so we've got no errors. So that's good. No errors means good. Quality, we're going to look at our mesh quality. Hashan would have taken you through mesh quality yesterday. The major one that we're looking at in Fluent is our minimum orthogonal quality. So that's basically, it's a little bit of a complicated formula that's based on the kind of face normals and the cells next to the cell that you're analyzing the quality of. But really, it's kind of like a measure of skewness, like an inverse measure of skewness. And the minimum orthogonal quality is 0.18 on this scenario in this simulation, which is good. So anything above 0.1, we can kind of rule out any problems later on due to mesh. That's kind of a rule of thumb. So 0.18 is quite a good quality. So we know we can go ahead with this mesh. Let's look at the size of the mesh, see how many elements we're actually looking at. So we're looking at just over 1 million cells. Okay, so quite a small mesh for an analysis like this, but it's just a representative one for us to get a simulation run today. So now that we're confident we have a high quality mesh and a relevant sized enclosure, we'll go through some of these other parameters. So in our solver settings, our general solver settings, we'll be using the pressure-based solver. That's what we use for most simulations. We can use the density-based solver if we're looking at high Mach number flows, so supersonic flows. Mach numbers above 3, we might use the density-based solver, but generally we're using the pressure-based. And we're doing a steady state simulation. So all of those we're keeping as defaults. Then we're going to come into here and we're going to look at these different models. The one of interest for us today is viscous, and basically that's just our turbulence model. Okay, I'm going to go through that in a bit, but turbulence, as a few of you, most of you will understand, is kind of chaotic flow phenomena. So it's really hard to pick up in a simulation. And to actually pick it up properly, you need to have a really, really super fine mesh. So what we do is we've developed methods of representing turbulence through a bunch of different models. Okay, the one we're going to set today is K omega SST, and that one's a well defined. It's been developed over many years by a guy called Florian Mentor, and they've done a lot of work in getting this model to represent reality at a higher level. And so what it does is it has an SST, which I'll take you through, which is the shear stress transport model, which can pick up what's happening in the boundary layer really accurately with minimal mesh elements. Okay, and this is a 2-equation model. Another similar one is our K epsilon model. And then as we go down the list, they become a little bit more intense. So we've got a 3-equation transition model. So that's like our K omega SST with an extra couple of equations to pick up that's this one, with an extra couple of equations to pick up the transition between laminar and turbulent in the boundary layer. Okay, then we've got our Reynolds stress, our scale adaptive, and as we go down the list, like I said, they become more intense and a bit more complicated. But with this case, we've got a K omega SST, and that'll allow us to pick up what's going on in the boundary layer quite well, which is really important for our simulation. Okay, we're going to look at our material. So in this case, we're just using air. So we've got our fluid domain. The only material we're looking at is air. We don't need to consider any solids because we're not doing a conjugate heat transfer. And we're not doing multi-phase, so there's only one fluid. Now, we're looking at a constant density. That's important because air is actually a compressible fluid, but it only is relevant to be a compressible fluid for the purposes of a simulation when we go above Mach 0.3. Okay, so when we go above 0.3 of the speed of sound, then we need to consider things like compressible gas, where we might do an ideal gas representation where we know PV equals MRT. That's the ideal gas equation. And that means we're solving for things like density. We need to make sure we have temperature turned on or energy turned on. In this case, because we're not solving any compressibility and we don't have any heat transfer, we don't need to have energy turned on, and we can have a constant density. So that simplifies things greatly. We've also got a constant viscosity. So there's a few models in here for variable viscosity, which you might need to have in situations where there's high temperature gradients or compressible flow. We can have a changing viscosity value based on some of these different models here. But for this case, it's very simple: constant density and constant viscosity. And we're going to look in here. We've got our zones, our different types of zones. Our cell zones are our volumetric regions. Okay, so we've got one cell zone, which makes sense because we've got one big fluid domain. If we had solids represented, or we had two different separate domains, we might have more than one cell zone. But in this case, one cell zone, and we can leave the settings for that default. Okay, there are some handy settings in here to have different types of mesh motion or frame motion. Frame motion is where we might have if we have a propeller that we want to run steady state, we might have that propeller set in a different cell zone where we put a frame motion on, and we say that this cell zone is rotating in this domain, and the rest of the cell zones aren't rotating. Okay. Mesh motion is similar. If we had a transient, you can actually watch that cell zone move time step by time step. But in this case, simple case, one cell zone, and it's not moving. So then from there, we're going to look at our boundaries. So we've got our inlet, and our outlet, that's good. Our inlet is a velocity inlet, so we've got direct control of what the velocity is coming in. There are some other options with that. We could do a pressure inlet, we can do a mass flow inlet. In this case, it's a velocity inlet, and let's make it 17 meters per second. I think that's about 60 kilometers an hour. Our outlet's a pressure outlet, and our pressure outlet should have a 0 gauge pressure in this case. And that just basically means there's no pushing or pulling from the flow. If there was a positive pressure, we're forcing flow back in or trying to push against the flow coming through. And if there's a negative pressure, it's sucking flow out. At 0, it's just like it's going out into atmosphere. There's no force on the flow coming out. Everything else we can leave constant. And here we've got our symmetry. Our symmetry is obviously on the wall of symmetry, on our symmetry plane. And basically that just means there's 0 gradients at the wall here, and there's no friction from the wall on the airflow. Okay, you can go into the help file if you want a better understanding of the theoretical representation of a symmetry wall. I've actually put symmetry on all the other walls as well. Basically, I just don't want these walls to interact with the flow. Because what happens when we have a wall, obviously we have a boundary layer, and that boundary layer means that the flow at the wall is essentially 0, which kind of reduces the size of the domain and increases the complexity of the simulation. We might run a simulation like that if we were doing a kind of matching up against some wind tunnel data. Right, if we wanted to actually model the whole wind tunnel, we might have walls on the outside of our domain that are the same size as the walls in our wind tunnel. But generally, we want to have either some kind of far field representation, some kind of maybe pressure outlet, something that's not pushing or pulling on the flow at all. And then the rest of these that we've got our walls. Okay, now all of these walls are 0 slip walls, which is just a standard wall, which means that the velocity, the relative velocity at the wall of the flow is 0. Okay, so we know in aerodynamics that any flow moving over a stationary wall is 0 at the surface, and that's what creates the boundary layer. Okay, as we move away from the surface, the velocity of the flow increases towards the free stream velocity. So our chassis is a stationary wall, 0 slip. Front wing will be the same. Our ground will be a moving wall. Okay, that's really important for an analysis like this, because we basically have, if we're trying to represent the car driving through the air at 60 kilometers an hour, that the wall, the ground needs to be moving at the same speed. And that's really important because it changes greatly what happens to the flow around the front wing and around the wheel. Okay, if we don't represent the flow properly, we're not going to pick up things like ground effect, etc. That's why it's hard to do accurate wind tunnel analyses of things like an FSAE car, because in a wind tunnel, unless you have millions of dollars, you can't really have a rolling floor, which means you're not going to get the same boundary layer effects, not boundary layer, so ground effect. Because when you have a boundary layer that grows on the floor here, because the flow is stationary, it chokes up the flow underneath here, and it's not representative of what's actually going to be happening when the car's driving along the ground. Thankfully, in CFD, we can put a moving wall in, okay? And we need that wall to be moving in -z. So we're going to change the direction of movement to -1z, and we're going to change the speed to 17 meters per second, the same speed as the inlet flow. Obviously, the other really important one to get correct if we're going to understand the flow around our front wing is the moving wheel, okay? And so we can have a moving wall on this one, but this time it's going to be rotational. We need to get this axis correct. So we're going to go back into SpaceClaim quickly to get exactly what that measurement is. So we've got out in X, Y, Z, we've got, it's going to be in Z, we're looking at a -899 millimeters. So -0.899 millimeters, making sure to be correct with our units. And our Y value is a positive, remember, because I've clicked that one first. So we're looking at the different reference frame. That's why it's negative, not positive. But in this case, we know it's positive because we can see 226 millimeters. So 0.226 millimeters. Okay, our rotation axis, if we do our right hand rule, should be stick our thumb out in X and rotate our hand. It's going to be a positive rotation in X. So we need to make that 0. And our rotation axis is positive about X. Now, what is this value of rotation speed? We need to know what the diameter of that is. So 457 millimeters. So let's calculate that using Excel. 457 millimeters, not 0.457. The speed is 17 meters per second. So we get this one divided by, so our velocity divided by our radius. So that should be our radius, shouldn't it? So equals that one divided by 2 because we're looking for radians per second. So this one should be equal that one divided by that one. So our radians per second should be 74.4. So we go back to Fluent. So we can see it's asking for the speed of rotation in radians per second, 74.4 that we just calculated. And now we've got a rotating wheel about our wheels axis, rotation axis origin, and rotating in the right reference frame. Okay, so that's all the boundary conditions. The rest are just normal walls. User defined, we can use this for things like UDFs, so user defined functions. They're little bits of code that we can enter into Fluent to do extra functionality. We don't need to do any with this. It's quite a high level function, but so if you get into CFD in your final year projects, you may end up using it. But we're not really going to cover it today. Now in our solution, we're going to look first at our solution methods. So we've got our pressure velocity coupling scheme. In this case, we're using coupled, that's default. And basically that just means we're solving our X, Y, Z velocities in the cells, in each cell, all at the same time. So we're coupling our mass and momentum. In these cases, they're called segregated solvers. So simple, simplex, piezo, all segregated solvers. So we're solving X, Y, Z separately. Coupled means it's going to take a little bit longer. It's going to use a bit more RAM because it's doing them all at once. But it means we get a much more stable solution generally. Generally speaking, it's a more advisable pressure velocity coupling method. Then we're going to look here, we've got our spatial discretization. Okay, so there's a couple of different gradient methods. We can look at Green-Gauss, node or cell-based, and least squares based. We're going to leave it as default, and you can go into the help. I'm sure Hashan showed you the Ansys help, ansyshelp.ansys.com. You should be able to go into there and search things like our gradient methods in Fluent. Okay, so you can go into here, you can get an understanding through either the user's guide on how to implement them, or there'll be some links to the theory guide as well. Okay, so evaluation of gradients and derivatives. Pressure, second order, momentum, second order, turbulence will generally come in at first order, and that's okay. So second order is slightly more accurate than first order. It does a better representation of the gradient at that cell, and I'll go through that in some slides. I feel like it's a bit better to look at the slides rather than just explain it to you here. You get a bit of a better understanding what we're talking about. And pseudo transient is now the default in Fluent as well. Pseudo transient's just a really good way of getting a stable solution for a steady state problem. In CFD, we're trying to understand highly nonlinear and highly transient phenomenon, usually in a steady state case, right? So usually for a case like this, it's going to be pretty transient what would actually be happening in reality. Even though you're keeping everything constant, the flow might be shedding off vortices off that front wheel with some given frequency, right? So what we're doing is we're trying to get a steady state solution, which is trying to get a time averaged sense of what's going on. Pseudo transient is just the method we use for that. And that gives us a couple of options in here as to either our timescale factor, or we can actually specify a pseudo transient time step size. Okay, so in here today, we're going to leave it all constant, not constant, default, sorry. And then we're going to look at our solution controls. Now in here, we've got what's called our under relaxation factors. Okay, and that's basically when you solve between iterations. So between iteration 1 and iteration 2, there'll be some different value of pressure at each cell, different value of momentum. Under relaxation, we'll use a percentage of that difference between the two values. So rather than, so we got P1 at iteration 1 and P2 at iteration 2, rather than going all the way to P2, well, you go halfway to P2. And what that does is it allows us to step more gradually towards the solution, and that can increase solver stability, okay, at the cost of solve time. So we're going to leave these as constant as default today. But if you have difficulties with convergence, or you wanted to speed up the convergence, you can change these. You can increase them to speed up convergence or decrease them to increase stability of solution. Now in here, we've got our reports, we've got our residuals, which will is the main thing that we look at generally when we are trying to understand convergence. So our residual is the difference between the left-hand and right-hand side of the equation, the Navier-Stokes equation. Okay, I'll just pull that up for you again quickly because it's, you know, it's the baseline for all CFD. So I'm sure Hisham went through it yesterday, but I'm just going to reiterate the points. So this is our Navier-Stokes equation. So this is the baseline for all CFD. We've got our transient component, we'll have our convection component, we'll have our diffusion component, and then our generation component. Now the transient and convection should equal the diffusion and generation. And the difference between those two sides means we're not actually quite converged. And the difference between those two sides is what we call our residual. Okay, so those are what we monitor when we set our CFD simulation to solve, and we're watching these residuals change with the iterations. We're hoping that they're dropping. We're hoping that they're going down, okay, because we want to see this get to 0, basically. We'll never get to 0, but you want to see it get towards 0. Okay, so these are our residuals. We'll have one for continuity, one for X, Y, and Z, and one for K and omega, because we're using the K omega turbulence model. So the more models you have turned on, the more different types of residuals you're going to have to monitor. And it says here that our absolute criteria is to get those residuals below a value of 0.001. Okay, we're going to leave that as default. So we'll watch those later on when we set this to run. Now, these definitions are very important. Okay, so these are a second way that we monitor convergence, and these can be very helpful because, once again, what are we trying to do? We're trying to get a steady state solution of what is often, what is always highly nonlinear, and what is very often a transient problem. So our residuals won't always behave in the way that we want them to, so we need to have a secondary method of understanding whether or not we're converged. And one of the ways we'll do that is we'll pick a quantity of interest. Okay, so our quantity of interest that we want to go through now is drag and lift, because that's what we're most interested in with this simulation. Okay, usually for a simulation like this. So we're going to create a drag report. We'll call it drag. We're going to make sure it's a force, not a coefficient, and we're going to use everything but the ground. And we want to make sure we're getting that vector in the right direction. So that should be negative Z. And what we're going to do is we're going to get a report plot and print as console. So the report plot will just mean that it'll show up in here as we're solving the iterations, and print to console means the values will show up in here. We can also create a file that we can post-process ourselves later, but in this case, we're not going to create one of those. So we've got our drag, and we want to do our lift as well. In this case, we're looking at downforce. So we want it in negative y, lift force on everything but the ground. So we're looking at the force, this summation of the forces on the wheel, suspension, front wing, and the chassis. And we're going to do a report plot and print to console with that one as well. Okay, so that's basically mostly set up now. We're really just going to initialize and set to run, and then we're hopefully going to come back and look at this simulation a bit later on today and maybe post-process some results, or troubleshoot if we don't get to the end. Now, initialization can be very important. So initialization is just your first guess. So whenever you can conduct any kind of iterative calculation, you need to start at some guess point. The closer your guess is to the final solution, the faster you're going to converge to that solution, and the more likely you're going to converge to that solution. Because if you start way outside the or very far away from the final solution, your start point can actually cause you to diverge. Okay, so there's a few different ways that we are initializing. There's your standard initialization. So standard's just going to put a value in all of the cells. So that's your simplest, easiest methods. It's going to start everywhere at 0 and 1 with kinetic energy and dissipation rate. So if I was to initialize that, it's just going to put that in all of those cells. A slightly better method of initialization is our hybrid. And that's going to run through about 10 preliminary iterations to try and get some residual below a certain value, and that's going to be our start point. If you want to know more about that, you can go into the theory guide again to know exactly what it's doing when it's doing a hybrid initialization. You can see here it's going to run through about 10 iterations. And that's going to give us some first guess at what the solution is in each of the cells. From this point now, because we have an initialized solution, which means we have solution values in all the cells, we can even post-process because we've got solution data to look at. So we can see our best guess is still not very close to our solution, but it is just a first guess. Another method of initialization is FMG. So if we were to go solve, initialize, there's a option for FMG initialization. So that's a slightly more advanced one. That's called something multi-grid. And what it does is it basically cuts down the amount of elements in the domain in sections and kind of gets you to a much closer first guess and first starting point. So it can be a really good method of getting a converged solution where you can't with other hybrid initialization methods. So we're going to go Q, enter, that takes us back. So in here, when you hit enter in Fluent, you've got these TUI commands. Okay, these can be really helpful because you can use these for scripting and things. Okay, so if I was to solve initialize, hyb initialize, I could just go solve init hyb init, and it'll know what I'm talking about. Yes. Right, so you can see that if you have a journal file with a bunch of these commands, you can import the journal file and it'll run through all these commands and automate things for you. Okay, so if you're doing a lot of different simulations, it can be really handy to build a journal file based on these TUI commands. And a TUI is a text user interface. Okay, that's why we call it a TUI, TUI, text user interface. Okay, so now we can set this to run. Our timescale factor is automatically calculated for our pseudo transient timescale. So if we look at our options in here, we get our time set method automatic. We're going to leave it at 1. So it's going to do a calculation based on the size of the domain, based on the size of the objects in the domain, the walls in the domain. And we're going to leave that at 1. If we see we're not converging, we can use that as kind of like another relaxation factor. We can change that to 0.1, 0.01, or we can even put a user specified, and that's going to give us the option to do a time step. So in this case, we're going to leave it at 1. We're going to run for about 200 iterations, and we're going to set that to calculate. Now, I will go to the slides for a little bit after this, but does anybody have any questions regarding that process so far? Okay. Yeah, Noor, you've got your hand up. Just chuck the message in the chat.
Okay, so I have just a question regarding the like the solver for steady state. So if we're looking into a moving object, are we going to be looking into a transient state, like a transient state model, solving for a transient state model?
Yes, depending. So like I mentioned before, I'm not sure if I have this case up. I do. Now I'll go through this in more detail later, but this is a propeller, as you can see, or representative propeller. And I'll show you the cell zone. So in this case, we've run a single cell zone, and this whole cell zone is set to be rotating. Okay, so we've got frame motion turned on. It's rotating about the negative y-axis at some velocity, some rotational velocity. Now, basically, because our external boundaries are just outlets, they don't have any effect on the flow. So the flow is still coming down basically straight without any of this having an effect, but the propeller is is moving in space at this rotational velocity. Okay, so in this case, we don't need to run a transient. So when we use frame motion, which is a moving reference frame, we can actually run a steady state analysis because of the cyclic nature of the propeller. The propeller is just going round and round and round in the same spot. When we have something that doesn't have a cyclic nature, or is moving in more complex ways, then we can do things like turn mesh motion on, okay? And that will be a transient analysis. So you'll need to capture that time step by time step because there's no constant nature to the way that that object is moving. Does that make sense?
Thank you.
Cool. All righty, Roberto, do you want to unmute or chuck it in the chat?
Yes, please. I always have a question trying to mimic real life on this sort of problems. So, for example, on your wing, on your example, you're going to have this wing moving up and down constantly, right?
Which one? On the car or this one?
On the car, on the car.
Yes, I mean, in reality, that might be the case.
Yeah, we have movable parts. So that's one case. In the other cases, for example, in a power plant, when you have heat exchangers, you're probably going to have the pipes expanding and some sort of reducing all the time. So is there any way to capture all these small movements that can affect the final performance?
Yeah, so we're basically looking to use engineering judgment as to when we can ignore them, because that greatly simplifies our analysis. Okay, so if we're looking at things like fluid structure interactions, which is mostly what you're talking about right now, you're adding in another solver, you're adding in a whole bunch more complexity and a whole much more computational resource. Absolutely, it is possible. So what we can do is in here, we've got what we call workbench. We would advise most of the time when we're just using Fluent to work outside of workbench. But if you wanted to do a system coupling analysis, what you can do is you can run in, you've got your Fluent in here, right? And so our setup's going to be our case file. Our solution is going to be our case file with our data in it. And that just means it's got some results in it. And what we can do is we can link in a system coupling, right? And now we've got our static structural analysis, and we can link in our static structural and our system coupling, and that's going to transfer data between our CFD analysis to our FEA and back from our FEA to our CFD. So CFD is going to be transferring pressure values, force values, and FEA is going to be returning things like thermal expansion or stress, not stress, but deformations.
Okay, great. Thank you.
No worries. Cool. All right, no more questions. We'll have a look at some of these slides. Kind of try and cover everything that I didn't get to. The first thing we're really going to be talking about is turbulence models. Okay, so turbulence. This is the $1 million question. It's the way it's been described to me many times, and I'm starting to get a good understanding of how that's the case now. This is absolutely the $1 million question when it comes to CFD. It's difficult to get a very accurate understanding of something when it takes such a high computational resource to do it. So we've developed, like we said, we've developed these methods. So when we're doing our modeling, and we're looking at our turbulence modeling, it's important to get it correct. All right, so we've got our 3 different flow regimes in this case that we're looking at. We've got our laminar flow regime where all of the lines in the flow field are kind of constant. They don't really intermingle. And we've got our transitional where things start to get a little bit wavy. Some of these lines are crossing over with other lines, and then we've got fully turbulent. And these are really highly linked to our Reynolds number. So our Reynolds number is a non-dimensional number that tells us a lot of information really about our flow regime, what's called our flow regime. Okay, and it's our density times our velocity times our given length scale over the viscosity of the flow. And so what it is, it's our inertial forces on the top divided by our viscous forces. So the higher the inertial forces relative to our viscous forces, so it's a ratio, the higher the Reynolds number. And the higher the Reynolds number, the more turbulent the flow. Okay. So turbulence is measured through the deviation from the mean velocity. Okay, so if we have a pitot tube in the flow here, and we're looking, so our pitot tube, that's like our reverse pitot tube. Say we're looking from the other side, we've got a pitot tube that's measuring the flow velocity. We're going to have a pretty constant value in our pitot tube. In this case, we're going to get a little bit more chaotic, and in this case, it's going to be all over the place. Okay, so this is what we would be looking at if we were measuring the velocity in any of them. Okay, it's always going to be a little bit up and down, but the more up and down, the more of the deviation from the average velocity, the higher the turbulence. Okay, so we've got our velocity as a function of time is our mean velocity plus some deviation from the mean velocity. Okay, and our actual value of how turbulent the flow is our root mean square of the deviation of the velocity from the mean flow velocity. Now here we're looking at a turbulent boundary layer on a flat plate. Okay, so we're looking at a wind tunnel experiment with some smoke. And you can see that they've tripped the boundary layer, and the boundary layer will always grow. So along any surface, boundary layer is always growing. And we're getting some turbulent effects. And you can see that as we go along, our Reynolds number is changing. And the reason for that, if we can capture that again, our Reynolds number changing here is if we go back, we remember what our formulation for Reynolds number is density times velocity times length. Our velocity should be staying same in that analysis. Our density should be staying the same unless we're above 0.3 Mach. And our length scale is changing. Okay, so we're getting further and further along the plate, and that's why our flow regime is changing. So what we're going to do is we're going to look at the other plates. So they've got a second plate. It's very cool how it all develops, how the vortices kind of develop. And this one's a higher velocity. Okay, so the plate's moving through air at a higher velocity. Our Reynolds number starts out higher and gets higher. And so you can see it's slightly different. And we look at the two in comparison with one another. And so we remember that the higher velocity will be a higher Reynolds number, and so that one was a higher probably a higher level of turbulence, you can see here. Now, a couple of important properties about turbulence that is something that they try and capture when we're doing turbulence models is that turbulence has a length scale. Okay, and you can kind of see that here. So the different turbulence values, different levels of turbulence, different Reynolds numbers have a different turbulent length scale. And those length scales are the diameter of the eddies, the vortices in the flow that contain the highest level of energy, the highest ratio of the flow, total flow energy. So you can see here that the eddies in this case are much smaller. And in this case, they're much bigger. So for two different flow regimes, we've got two different levels of length scales that we would be really interested in picking up. Okay, so when we actually want to pick up turbulence directly, it's really important that we're picking up the highest energy length scale. Okay, and then what happens in a turbulent flow field is you have these eddies that kind of dissipate into smaller and smaller eddies. So you have the biggest eddies in the flow and they break down into smaller and smaller eddies. And that's basically the way turbulent flow works. So 3 different main computational approaches to resolving turbulence. The first one is DNS, which is direct numerical simulation. And you can see that is the most involved, that is the most involved. Second is LES, which is large eddy simulation. And the third one is RANS, which is our K omega model. And that's just getting a averaged kind of representation of what the actual eddies are doing. So you have things like our turbulent kinetic energy, rather than actually directly modeling the kinetic energy. So when you're modeling the velocity of this eddy directly, you're actually just modeling the velocity is the kinetic energy. When you're not modeling that kind of swirling flow, you have to have a representation of what the turbulent kinetic energy is, and that's our K value, K omega, in the K omega or K epsilon. And things like eddy viscosity ratio you'll have in here. So our eddies are actually directly picked up in here, but in here we have our eddy viscosity ratio. Okay, so those are the kinds of parameters that they're using to represent what's actually happening. Now, DNS is actually just solving our Navier-Stokes equations. It's not a model. So when we solve our Navier-Stokes equations directly with really, really, really small mesh sizes and also a higher order spatial discretization, so that's really important as well. When we have a higher order spatial discretization, it gives us more accuracy. You can then pick up direct numerical simulation. Now, this isn't really used anywhere other than academically. Okay. And that is because of the excessive computational resource that it requires. The large eddy simulation is the next level. That one is sometimes used in industry, and I'll show you a model actually that I did to help with the support case. I just built a representative case, and what this one does is it tries to pick up the larger length scales, so these ones, but it doesn't pick up the smallest length scales. And that's really important because obviously if you're picking up those small length scales, say you've got a vortice that is, a few microns across, you want to have at least 10 mesh elements across that vortice, because that's going to help you pick up the swirling flow. If you don't have multiple mesh elements across that vortice, you're not picking up the swirl. You're having some averaged velocity in one single given direction. Okay. So that's our large eddy simulation where we pick up the largest but don't worry about the smallest, and that is a model. There are some things that help to represent the actual dissipation of eddies. Okay, so that energy needs to be the energy dissipation between the largest energy eddies and the smallest needs to be modeled rather than picked up directly. And then our RANS, which we're using for most analyses. It's the most widely used approach for industrial flows. Okay, RANS modeling. All turbulence effects are modeled, like I said. So rather than having actual vortices in the flow, you've got your kinetic energy, your K value, and you've got your turbulent viscosity. These are the ones that we went through. Our stress blended eddy simulation is one that is a really important one here. And I'll take you through the setup of that one just really quickly, and then I think we'll have a little break. Okay, so this is effectively, I'll show you the full domain. So we've got our inlet on the left and our outlet on the right. And what we've got is we've got a flow coming in, has to go through these channels, and then it goes out to the outlet. In reality, what this is trying to represent is a sleep apnea mask. Okay, so as the person's breathing into this side, it's going out to the atmosphere on this side, which is through outside these holes. So as soon as it's out of these holes, it's basically into atmosphere. And what they were looking to do is to model what the pick up and analyze what the actual noise being produced was. Excuse me one moment. Yeah, so they want to pick up the aeroacoustics based on the noise that was being produced by these sleep apnea masks, because obviously you can't sleep very well if that's the case. And so what happens in that case is you have the flow comes in, it gets squeezed through these channels, it increases in velocity, and then as it leaves these, it becomes turbulent. Okay, and that turbulence creates pressure fluctuations, and that's what sound is, right? So sound is pressure fluctuation. So in order to pick that up, we really needed to pick up some of the actual turbulent length scales to see what the pressure fluctuation was in those regions. Okay, so we'll quickly run through what the setup is. We'll assume our mesh is good, got a decent size, high quality. We will actually just quickly look at one of the planes, just so you can get an understanding of how the mesh was built and why. So you can see that we've got a really high mesh density in our region of interest. Now, what's really important about our stress blended eddy simulation is we're using large eddy simulation, which is our LES model, which was this one here, our large eddy simulation in the middle. And stress blended eddy simulation is using that and RANs at the walls, okay? Because at the walls, in reality, there actually quite a lot of turbulence in the boundary layer, and we'll go through that in a moment. But instead of modeling that directly, we want to have a stress blended. So we have LES in the middle where it's important, and RANS models at the wall, a K omega at the wall. Okay, so that's why we have a really high mesh density in here. And the setup for this one is our pressure based, because we don't have any compressibility effects, or we don't have above Mach 3, sorry. So Mach 0.3 to have compressibility effects, but you can still have the pressure based solver. Mach 3 to have the density based solver. Okay, hypersonics kind of territory. And it needs to be transient. Okay, because when we're doing turbulence, obviously that is probably the most transient phenomenon. It's chaotic and it's moving all the time. There's nothing stable or constant about it. And in this case, to set up a stress blended eddy simulation in our viscous models, our turbulence model, we're turning on our K omega SST, and then there's an option to have stress blended eddy simulation or shielded detached eddy simulation. So SBES, we turn that on, and then we have our subgrid scale model. So subgrid means below the length of these grid sizes, these element sizes. And that's important because we're picking up the largest eddies, but not the smaller eddies. So we're modeling the dissipation energy, the energy dissipation from the larger eddies to the smaller ones. And that's we're using the whale method. Once again, go to the help if you're interested to find out more about the theoretical formulation behind that. So we've turned on K omega SST, we've turned down our stress blended eddy simulation, and then we're going to run this a few time steps. So we're going to run that transient number of time steps. Now, one of the things that it's really important to do when we're running any transient analysis, if we can, sometimes it's not possible because we really have some stationary start point, But if we have a really good steady state approximation to the start point, it's a much faster way for us to start to get a transient solution. Okay, and what I mean by that is rather than running transient, we'd start with a steady state simulation. We've got one steady state solution, and we've got a solution here already for that. Okay, so we can see here, this is run just K omega SST, steady, right? And that obviously you can see here, we've got our flow coming in. There's not really any kind of chaotic phenomenon being picked up. And then we turn on, that's our start point. So we've got this solution in here. We turn on our SBES, and then we run transient from that point. Quickly check our methods. So in this case, we're using simple. That was because of an increased stability of using simple and reduced RAM for this case. Now remember the difference between our simple and our coupled pressure velocity schemes. Coupled is where we couple mass and momentum. So it can use more RAM. Let's go back and I haven't actually been through it yet. I've just mentioned it, but here we go. So we've got our pressure-based versus density-based. And our coupled versus segregated. Okay, so just to quickly touch on, because I don't feel like I'm going to get through all these slides today. Segregated, we're solving U, V, W, X, Y, Z momentum, so mass, velocity. Separately, and then we're bringing in to solve energy, species, etc. In our coupled, we're solving mass, momentum together. Okay, all of those in one calculation and then through. So in this case, we've got our simple. We're using first order implicit transient formulation, and then under relaxation factors, remember that they are our difference between our iteration 1 and iteration 2, whether we go all the way to the calculated pressure value or all the way to the next calculated momentum value, or we take some fraction of that to increase stability. And then we run this for however many time steps at whatever time step size. Time step size is obviously quite small, so 4e⁻⁵ seconds per time step, and that's pretty indicative of most transient flows. I mean, you might be able to get a few orders of magnitude better than this, but especially for a case where you're trying to pick up pressure fluctuations for the purposes of a noise analysis, right? Because at the level of fluctuation or the time scale of those fluctuations is going to be very small because we're looking at kind of sound pressure waves, right? And so one of the things that we would do in this case is we would create a point somewhere in the flow field where we're expecting to get turbulent phenomenon. We'd create that, and then we'd create a monitor point of a vertex maximum pressure. So vertex maximum pressure at that point, okay? And then we'd take out our report file and we'd save out the file of that, because what we want to do on that is we're going to get some time value of pressure, right? It's going to look like up and down all over the place. And then we can do an FFT of that. Which Fluent has built in here. So an FFT analysis, and that's going to tell us what the decibel level, the actual decibel level, and what frequencies are being produced in terms of those pressure-based sound waves. Okay, so I'll show you a animation of the results of this one. So we've got 500 frames, animation 1, which is velocity. So you can see once we turn transient on, takes a little minute for it to start to resolve that. We're going through these frames. You can see there's a little bit picking up here, and then you can see it's tripped. Okay, now that it's tripped, okay, we've got kind of turbulent flow. So it started to kind of shed vortices because we've got kind of a shear stress layer between our stationary flow here and our jet stream flow here. And so if you can imagine a point in the flow here, the pressures at that point are going to be fluctuating, and that's going to give us an understanding of what kind of noise we're going to be getting out of a mask like this. When we run our FFT, that tells us the decibel level and the frequencies, which frequencies of noise that we're going to be hearing. Okay, so we'll probably take a little break now, 15-minute break. Does anybody have any questions regarding what we've just gone through? Turbulence modeling. Okay, yeah, let's take 15 minutes and I'll come back and we'll go through some more turbulence. We're going to look at, when we come back, we're going to look at picking up the boundary layer, which is really important, especially for external aerodynamics, but really for anything, and also heat transfer. So it's just something to really, it's really important that you understand if you want to be a good CFD engineer. And then we're going to also look at heat transfer. We're going to look at some of the solver settings again, and then maybe we'll be able to come back to this this model here and try and ascertain whether or not we've got convergence and maybe do some post-processing on that as well. Okay, all right, I'll speak to you guys in 15 minutes.